Welcome everyone to the webinar, Design of Bolted Connections per the 2015 NDS. And this is copyrighted material, but if you're interested in using parts of the presentation, we have a policy that allows for that, and so you can contact us for more information. This presentation is also registered with AIA, and so if you are seeking AIA credits, Marcy and the rest of the team can help make sure that that happens for you as well. This is the description of today's webinar that you've hopefully seen already as you signed up, but we're going to be using the 2015 NDS today for this design example. And don't worry if you're still using an older version of the code. A lot of the table numbers and things like that are very, very similar to what you'll be accustomed to. I'll point out those differences for you. The topics will include a little bit about philosophy and behavior, an overview of the provisions related to connection design, and then we'll look at Appendix E of the NDS, which deals with local stresses and fastener groups. And we use a detailed example to accomplish that along the way today. So hopefully at the end of this webinar, you'll be able to understand the yield limit equations for dowel-tight connections. You'll know when to utilize the appropriate adjustment factors, and apply spacing in and edge distance requirements, and then again determination of local stresses and fastener groups. So before we get started into all that, I'll ask Marcy to come back for our first and easiest poll question of the day, because there are no wrong answers for this one.
Absolutely. All right. So what is your profession? Architect, engineer, code official, building designer, other? So I'll give you about 30 seconds, 30 to 40 seconds to answer. And this one, you know, participation is key here. So if you want to earn that, a chance for that publication, participate. All right, so 82%. I'm going to give you about 10 more seconds. All right, I'm going to assume that all of you have voted. So we have 80% engineers, 12% code officials, 4% architects, 3% building designers, and 2% other. All right, welcome everybody.
All right, great. Yes, and welcome. So let's then start off with a little bit of a philosophical discussion of connection design. And to do that, we'll want to start first talking about the wood members or the lumber itself. And you may have seen this before, but this is a helpful analogy where you could conceptually model wood cells as a bundle of straws. If you were to look microscopically at inside of a 2x4, you'd see long strands along the length of that 2x4 parallel to grain that look something like straws. And so parallel to the axis of those straws, either in tension or compression parallel, wood is very strong. In the other direction, however, whether we're talking about compression perpendicular to grain or the opposite, which is tension perpendicular to grain, wood is less strong. In fact, tension perpendicular to grain is sort of the Achilles heel for wood members. And there are reasons for that, and that gets into wood science, which we won't do here today, but it has to do with the way those fibers are bonded together. And so we're going to avoid situations as much as possible in connection design that would create tension perpendicular to grain stresses. and try and get more bearing on the wood members. You'll also see this played out in the dowel bearing strengths of wood members, in the difference between the dowel bearing strength parallel and perpendicular to grain, and we'll point that out too as we work through the design procedures today. But the other thing about connection design is that wood likes to take on load that's spread out over its surface rather than concentrated in one location. So we're not saying that you cannot design a connection with a single, large single bolt, but if you have a choice to use a lot more smaller fasteners versus fewer large fasteners, that should be your preference. Connection design can be as much an art as a science, but that's sort of an underlying philosophy if you're new to connection design that you may want to be aware of. And so there are lots of different types of fasteners, obviously covered in the NDS. We're going to look at bolts today, but again, this is sort of one of those philosophical approaches to connection design. So when you jump into the NDS, and note in red here, we talk about the new chapter numbering for the 2015 NDS. Let me try one of these new pointer tools. Somebody commented that they were having a hard time seeing. So you see the blue arrow there. We've got new chapter numbering for the 2015 NDS. And so when you may be used to seeing this table as 10.3.1, it's now in chapter 11. We've added a new chapter 10 for cross-laminated timber, and so that sort of shifted all the connection chapters up one. So this table, 11.3.1, covers the adjustment factors for connection design. I forgot to mention that NDS is both allowable stress design and LRFD, and we cover several different types of fasteners. We'll be looking at dowel type fasteners today, but we also cover split rings and shear plates, timber rivets and spike grids, very sort of niche type fasteners that aren't used a lot, but that's what's shown here in this table. And so as we look today at some of the adjustment factors, the applicable adjustment factors for connection design, for dowel type fasteners, that's going to include the load duration factor, the moisture factor, temperature factor, group action factor we'll actually calculate today, geometry factor we'll calculate today. For certain types of fasteners, like split rings or wood screws and lag screws, there's an end grain factor. For nails, there's a diaphragm factor and also a toenail factor. So some of these are very specific to certain types of connections and don't necessarily apply. And we'll take a look at that in a few slides later to see exactly which ones apply to bolt type connections. So on this screen, what you're seeing is a reference to section 11.2.2, again, new numbering in the 2015 NDS for multiple fastener connections. And what that says here inside this red box is that local stresses in connections using multiple fasteners shall be evaluated in accordance with principles of engineering mechanics. And the test results there on the left in the figure show a chunk of wood being torn from the wood member due to a group of bolts that was tested in this glue lam beam. And so we're going to look at this approach to connection design today, because sometimes that is overlooked. But net section properties are very important to connection design, and the individual design values that you pull out of the table do not account for net section properties of the wood members, those local stresses in connections. And so that's a very important consideration that we'll look at, and you'll see how that can control the design process. Here's a few of the properties that we'll be looking at when we do that design later on. We'll look at net section tension capacity, row tear-out capacity, and then a group tear-out capacity. And you see some of the figures here on the right that show or model how we're going to look at that. And so we'll get into a little more detailed example here in the next few minutes. But then we get into NDS chapter 12, and that is for dowel type connections. And again, it's a new location, but our dowel type or dowel shaped fasteners include bolts, slag screws, nails, wood screws, spikes, drift bolts, and drift pins. The drift bolts and drift pins are really nothing more than large dowels without heads or nuts on the other end. And so there's a reduction factor for drift bolts and drift pins should you choose to use those in the design process, because there won't be a head on those particular fasteners. But again, today we're going to focus primarily on a bolt design example, but just so you know, the chapter applies to lots of different types of connectors. So when we start looking at different yield modes, and in the NDS provisions for connection design, there are various yield modes that you look at to determine what would control for various different types of connection geometry. So different diameters of fasteners, different specific gravities of wood members. We're connecting wood and steel and concrete in certain types of fasteners. So these yield modes are kind of broken down this way. What we call mode 1M or 1S, that's shown here inside the red box, is a bearing dominated yield of the wood fibers. And so you see to the left of the dowel here in the 1M figure, to the right of the dowel here in the 1S figure, it's showing crushing of the wood fibers. And so that's a bearing dominated yield, and we'll need a dowel bearing strength to determine capacity for that particular fastener. It applies to both single shear and double shear connections. So we're showing single shear here on the left, double shear on the right, and so 1M, the M in these examples apply to main member versus the S, which applies to the side members. So we're going to be checking both the main member dowel bearing capacity and the side member dowel bearing capacity for, again, for both single and double shear connections. So that's your mode 1 yield mode. Mode 2 then is a pivoting of the fastener with localized crushing. So we still have a large enough, stiff enough dowel that it's not yielding yet, like we'll see in a second. And so we've got localized crushing here, you see in blue on sort of the edges of the wood members. And so that's characterized as a mode 2. And we've seen all of these yield modes borne out in the testing that was done to develop this methodology. When we get to modes 3 and 4, we start to see a much more ductile connection. And so one of the great things about these yield limit equations is it does allow you to build in ductility into a fastener if you want to deal with wind or seismic loads and have additional ductility in the fasteners. You can design in a mode 3 or a mode 4 control, and that's really what you're going to be seeing in a shear wall type of fastener. A nail is going to typically be a mode 4 or mode 3 type of fastener that has a lot of yielding in the dowel. And so for mode 3M, you've got that hinge forming in the dowel as it rotates through the main member. Mode 1S, you've got that hinge forming, a single hinge, as it rotates through the side member. And again, that bears out for double shear connections in this way, and you can see it graphically. When we get to mode 4, then it's almost purely a fastener yield driven connection. And so for single shear, we've got hinges forming on either side of the shear plane, some localized crushing of the wood fibers, and for double shear, you've got that same, 2 hinges forming on either shear plane, and so again, the most flexible, energy absorbing type of fastening approach there. So besides the equations, then we also have tables in the NDS where those different configurations of different types of fasteners where we tabulate design values. And so you need to pay close attention to the assumptions. One of those assumptions is that the faces of the connected members must be in contact. So if you have a gap between the side and the main member, that really kicks you out of the NDS into another technical document that we'll talk about a little bit later, Technical Report 12. And also that the load acts perpendicular to the axis of the dowel. And so you see the dowel here is normal to the axis of the wood members. Now, we can look at different angles to grain, but the load is parallel to, perpendicular to the axis of the dowel for these tabulated values. There are other ways to calculate at an angle that's not parallel, but for the tabulated values, those are some of the assumptions. We'll look at how we use these tables for the design example here in a second, so I won't spend a lot of time defining a lot of what's going on here in this table. So here's what those yield mode equations look like, and for single shear there are 6 of those yield mode equations, and they're labeled 1M, 1S, 2, 3M, 3S, and 4, just like we saw in the drawings earlier. And then for double shear, we've only got 4 equations because you don't get a mode 2 or 3M for double shear connections. And as you calculate these various yield modes, the lowest one is the connection capacity. So you'd calculate all 6 for a single shear, take the lowest one, and that's actually what's tabulated. I'll back up to the slide here. What's tabulated here in these tables is the lesser of those 6 yield modes for this single shear connection. So we've already done the math here and tabulated those values for you. If you're calculating them in a spreadsheet, then you want to take the lowest of these that are calculated. So 4 modes of failure, 6 yield equations, single and double shear. I mentioned wood to wood, wood to steel, and wood to concrete connections are possible and are tabulated in the NDS tables. And so you can pull those design values from the tables, or you can use the yield mode equations as shown here. So there's a lot of variables, a lot going on in these equations. Where do you find those variables? Well, it's defined there in Chapter 12. D is pretty straightforward. That's the diameter of the fastener. F sub YB is the dowel bending strength. We'll talk about how you can determine those capacities. A lot of them are represented in the footnotes. R sub D is the reduction term. There's a table that shows the reduction terms. We sort of hesitate to call those safety factors because there's a lot more to it than just a pure safety factor, but many of those reduction terms are going to range anywhere from 2 to 8 for different types of dowel type fasteners. The commentary gives you a lot more background on what it actually makes up those reduction terms and what the true safety factor is. L sub M then is the main member dowel bearing length. You see that pictured over here on the right, figure 12C. L sub S, the side member dowel bearing length. Then F sub EM and F sub ES are the dowel bearing strengths. EM would represent the main member dowel bearing strength, ES the side member. This table below here, 12.3.3, kind of goes back to our discussion about parallel versus perpendicular to grain properties. And you can see that the example we're going to look at in a little bit is a southern pine example with a specific gravity of 0.55, so I thought I'd pull that here to demonstrate. We're going to look at a 1-inch diameter fastener for our example. FE parallel to grain, whether we're talking about the main member or the side member, is going to be 6150 psi. Now if we were to look at a perpendicular to grain dowel bearing strength, and again that's the crushing strength of the wood fibers, for a 1-inch fastener over here all the way to the right under D equals 1 inch, it's 2550, so much less than, or yeah, a little less than half of the capacity for parallel to grain. So there is a difference, parallel versus perpendicular to grain, for these dowel type fasteners once you're above a 1/4 inch diameter. Less than a 1/4 inch, we don't see that difference between parallel and perpendicular to grain. So for nails and a lot of smaller diameter wood screws, less than a 1/4 inch diameter, you've just got one dowel bearing strength that you see here, 5550. So that kind of helps you navigate some of those tables, some of those properties. I mentioned the bending yield strength, and this is purely a moment capacity of the fastener itself, of the dowel. And we've looked at different steel standards, and if you look at Appendix I of the NDS, you'll see this table, I1, which lists some fastener bending yield strengths for various types of fasteners that are shown here in this table. What we assume for bolts and lag screws is 45,000 psi. And that's an average of tensile yield and ultimate strength of those fasteners. So there's more background in Appendix I that'll talk you through that. If you know you've got bolts or lag screws or other fasteners with higher capacities, you could certainly plug those into a spreadsheet and use those for your calculations, but that's what's assumed throughout the NDS for a dowel bending strength. So when we talk then about the diameter of the dowels, when we have threaded dowels, there is obviously a difference between the shank diameter and the root or threaded diameter of a lot of fasteners. And so what we assume also in chapter 12 is that we're going to use the root diameter or the thread diameter when the shear plane passes through or near the threads, like the drawing shown here on the left. And we're going to assume the shank diameter D when the threads are at least 3/4 L away from the shear plane, as shown here on the right. And so the technical report I alluded to earlier, technical report 12, we'll show you a link to that later on in the program, can be used for a more analytical approach, but this will help you understand some of those assumptions for D versus D sub R. Appendix L then of the NDS has some of the typical dimensions for dowel type fasteners. In this table L1, one of the first tables in that appendix, has the standard hex bolt dimensions from ANSI ASME B18.2.1, and we see again all the way over here on the right for that 1-inch diameter dowel that we're going to be looking at, some of the dimensions for that particular dowel. So the other thing that it should be helpful to you is spacing end and edge distance requirements, and this figure 12G of the NDS shows pictorially what we're talking about when we're talking about spacing between rows of bolts. You see the load cells here on the ends loaded parallel to grain. So spacing between bolt rows, the end distance, whether we're talking about a loaded end or an unloaded end, spacing between bolts in a row, edge distances. So this shows that parallel to grain loading where all the wood members are loaded up parallel to grain. And so you'll see in the headers of the tables these designations, Z parallel, this one is ZS perp, and what that means is that the side member is loaded up perpendicular to grain while the main member is loaded up parallel to grain. You'll see a ZM perp, which indicates that the main member is loaded perpendicular to grain while the side member is loaded up parallel to grain. And then the fourth option is what we call Z perp, and that's when both the main and the side members are loaded up perpendicular to grain. Think of this particular diagram here on the left as a ledger type connection, maybe with only two members where you're loaded vertically here, and so the main and the side members are loaded perpendicular to grain. So when you see those headers in the tables, that'll give you a little more understanding of those different tabulated values. And again, we've done a lot of the calculations already for a lot of those values, but you're going to get a chance to look at those in more detail as we work through the seminar. So I'm going to bring Marcy back and we'll take another poll question here.
All righty, here we go. So the NDS yield limit equations consider which of the following conditions? So is that A, wood to wood, B, wood to steel, C, wood to concrete, or D, all of the above? All right. And remember, the more you vote, the more everybody votes, the better chance you have.
Marcy, I've got an audience view showing up here that's still kind of stuck on my last slide, so I'm not sure that the audience is actually seeing the poll.
Well, I've got 67% voting.
Oh, good. Okay, good.
So
and that's great.
So
they are seeing it. That's great.
So. All right. I'm going to give you about 5 more seconds, and then, all right, closing. All right, we are split a little bit. We've got 78% say all of the above, 17% say wood to wood, 4% say wood to steel, and nobody says wood to concrete.
Okay.
So tell us what the answer is.
So the correct answer is all of the above. So a couple slides back, I mentioned the yield mode equations, 4 different yield mode equations, 6 of those specifically for single shear, 4 for double shear, and that we cover wood to wood, wood to steel, and wood to concrete. And those tables actually show up in the NDS. We've got tabulated values for all of these various types of connectors. So hopefully that's helpful to some of you that maybe weren't aware that we had wood to steel and wood to concrete values, and that you're able to use the yield limit equations for that as well. So we're going to jump next then into our design example, and who we found, and we get these comments back all the time that we'd love to see more design examples, and so that does give us a chance to give some practical application to this. It is a pretty simple, straightforward example. We're going to see what the capacity of this tension splice is. So this is a double shear tension splice. Think of something like the bottom chord of a truss. And we're going to assume 1-inch diameter, 5-inch long bolts, and 2 by 12, number 2, southern pine main and side members. So for you folks on the West Coast, Doug fir would probably be comparable. I think the specific gravity on Doug fir is 0.5 versus 0.55 that we're using for this example. We're going to look at a controlling load of dead and construction live. So No snow loads on this one. We'll be using a little bit higher load duration factor for a dead-end construction live load. And we're going to look at a normal moisture and temperature environment. And so we'll define that a little more too as we get into this. But you see the picture here, the spacing, end and edge distances that we've chosen for this particular case. This part of the example can also be trial and error. Because if you get your edge distance or end distances or spacings too small, you're going to get some reductions in some cases. When we look at the net section properties a little bit later on, that can affect the outcome, and so there may be cases where, again, spreading out the fasteners in a lot of cases is better than sort of locating them all real close together. But you may be constrained by the depth of the wood member in certain cases or the length of the splice that you have available. So those are all part of the consideration in connection design, but this example will let us kind of work through some of those. So we're going back to table 11.3.1, and we talked a little bit earlier about this, but for bolt design, there are a couple of factors that we can rule out right away. The end grain factor, the diaphragm factor, and the toenail factor. All three are not applicable. If you look at the footnotes, you'll see footnote 3, I think, sort of clearly defines when and where those are applicable for different dowels. But the other factors here that are shown, and we're going to do an ASD example. We're not going to do an LRFD example. So we're going to use the load duration factor, the moisture factor, temperature, group action, and geometry, and at least consider whether those can affect our design. So we're going to calculate a Z value, that's an unadjusted value, and then we would multiply those by these adjustments. So this next slide then, it has to do with the load duration factor. And in 11.3.2, in that chapter, it refers back to table 2.3.2, and that's where a lot of the frequently used adjustment factors are located in the NDS. And we said we have a construction live load that controls, and so we're going to use a 7-day load duration factor, which is 1.25. And you see the other load duration factors that are shown here for other types of load duration, but they do apply to connections as well as wood member design. The only caveat here in the footnote 2 is that the impact load duration factor does not apply to connections. So you could not use a factor of 2 for connection design. So up to 1.6, and so if you're doing wind and seismic design, you can use that 1.6 load duration factor for connections as well. This particular example, we're going to go with 1.25 for a construction live load example. So wet service factor is used if the moisture content varies from time of fabrication to when the fastener would see load in service. So this table 11.3.3 is used to determine wet service factors. And you can see that for certain cases, let's say you go in with a moisture content greater than 19% at time of fabrication, and then it dries down to less than 19%. Depending on the configuration, if you have a lot of bolts in a certain configuration, you can get a pretty significant penalty there, up to 60%. Now there are some caveats that allow you to back that off to about a 0.7 factor. Again, look at the footnotes, look carefully at those, but a lot of cases this has to do with shrinkage of the wood member, and again we'll look at some of those considerations. But in this particular case, what we're saying is that we're not going to have we're not going to have one of these cases where we're greater than 19% moisture content. So we're coming in at or below 19% and staying there in service, so we're not taking a wet service adjustment factor. So it's set to 1. Temperature factor, again, similar to wood members. If you have conditions up to 150 degrees Fahrenheit, and these are sustained temperatures. These aren't temperatures that you get, say, in an attic space where you heat up during the day and then cool down at night. These are sustained high temperatures. You see that it's even more pronounced in wet environment versus dry environments. We saw a lot of this information developed when cooling towers were being used, wooden cooling towers were being built and used, and probably are still used today. But the cooling tower industry did a lot of the research that is captured here in these factors. And then we've got something called the group action factor. So what the group action factor accounts for is load distribution within the fastener group. So this is kind of a monster equation here that you see. There's a lot going on here. It's probably one of the more nasty equations that we have in the NDS. And if you want to program that into your spreadsheet, have at it. I ran through the calcs before the webinar to make sure that I at least did a check and could say that I used the calculated method. So for this particular configuration, we came up with a group action factor of 0.97. So again, what that accounts for is the load distribution within a fastener group. So once we put that tension splice in tension under load, some of the fasteners at the end or closest to the splice may pick up load before it gets distributed off into the other fasteners a little bit further away because of construction tolerances, the oversized holes that are drilled. You could get fasteners that are picking up more load before the whole thing actually sort of begins carrying the total load it's designed for. So that's really what this group action factor is meant to account for. If you don't want to use the equation, there are actually tables in the NDS, and based on the number of fasteners in a row, which in our case is going to be 3 in each row. We've got 6 on either side of the splice. And based on the E value, the modulus of elasticity of the wood member, and then the gross cross-sectional areas of the main and side members, you come into this table and you actually end up interpolating 0.97, which is exactly what we calculated with the calculation method. So again, you can program the equation, but the table's here and allows you to pull those values out of a table. And again, as the number of fasteners in a row increases, we're here at 3. As it goes up here, as high as 12, you see you get a much larger penalty for this group action factor. So this is part of that sort of art or iterative process where if you use a lot of fasteners, you might get a little more of a penalty with a group action factor and have to, come back and try something different if it's not going to get you the capacity that you need. In this case, 0.97 is not a huge penalty. So the geometry factors then account for edge distance requirements, end distance requirements, spacing. The edge distance in our case is 3 5/8. You have to know in this case the L over D ratio of your bolt, and you're going to use the lesser of the main member to diameter, the length of the fastener in the main member to the diameter ratio versus the length of the fastener in the side member to diameter ratio, and whichever one of those controls you'll use. But we end up being okay. We've got enough edge distance there with 3 5/8, we only end up needing 1.5 inches. The spacing between bolts is 4 inches, and you see here for parallel to grain in this table that the minimum spacing is 3 diameters. The minimum spacing where you don't get a penalty is 4 diameters. So if you end up somewhere between these two, you get a penalty. But 3D is the absolute minimum. We're okay there. The spacing between rows in our particular case is 4 inches, so that ends up being parallel to grain 1.5 diameters, so we're okay there with our minimum spacing. But pay attention to some of the figures and text, because there's also a maximum spacing for outer rows of bolts in the NDS, and for wood members that's less than 5 inches. And so what that accounts for is shrinkage that can occur in these wood members. Let's say these are steel plates here on the side that are used in this particular fastener, and you've got a wood member behind there. So as this wood member, even if we come in at less than 19%, which we said we are in this particular case, we're going to dry down to an equilibrium moisture content of somewhere around 10%. And so the rule of thumb is that for every 4% change in moisture content, you're going to get a 1% change in the dimension of this wood member. And so what this 5-inch spacing does is it prevents you from getting into situations where you put additional tension perpendicular to grain stresses on the wood member, where you've got, say, steel side plates holding those bolts in one location, and the wood member starts to shrink down and try and pull those wood fibers apart. And so some of these dimensional limits here, like this one, are just meant to preclude you from getting into a bad situation where that could occur. So there are reduction factors for when you have higher moisture content. We looked at that earlier. That's the wet service factor. But there's also detailing that goes into keeping certain details from causing problems in the fastener. So in this case, we don't take a wet service reduction, but we are going to limit the dimension between those outer rows to 5 inches. And we're okay there too, because we're at 4 inches. So this next one, though, ends up being a reduction for us. So this is the end distance, and we're going to have to look at that cross section. And if you're referring back to the drawing, it's on page 23. You see that we have main members and side members with different end distances. So we're going to take the one that controls, because I think the side members have a 7-inch end distance on the loaded end, and 4 inches in this case for the main member. So we're really looking at the main member in this case. And so the absolute minimum, we're okay. The absolute minimum is 3.5 D. Oops, sorry about that. And we're at 4 inches, but we're less than 7 diameters, which means we have to take a reduction. So it's going to be a straight line reduction between 3.5 D and 7 D. So we're going to go with the dimension. That end distance of 4 inches over 7 gives us a 0.57. So that's the geometry factor for this particular end distance reduction. So we've worked through all the adjustment factors, and now we're going to work through actually calculating a Z value, an unadjusted Z value for a single member, and we come back to the yield limit equations. We're going to check 1M, 1S, 3S, and 4 because we're in double shear, and so those are the 4 that control. You can see how they're calculated here, and you take the smallest one, the least value controls, that ends up being your Z value. And that, again, is what's tabulated for us. I think that might be the next slide. So if you don't want to run through the calculations, if you're variables that you have end up showing up in a table. For us, it's 0.55 for southern pine. We've got a parallel to grain load configuration, 1.5 inch to 1.5 inch main and side members, a 1 inch bolt diameter down here. We see that capacity's 2310. We round to the nearest 10 pounds in this table. And so, again, we talked earlier about different configurations where you might have cases where the side member is loaded perpendicular to grain or the main member loaded perpendicular to grain. Again, we've tabulated those for you, but in this particular case, we've got a value of 2310. The other tool that's pretty useful if you're not aware of it is an online calculator that we have. And so what I've shown here is using that online calculator. The link's there on your slide. You can check that out on your own. But for a allowable stress design, lateral load, bolts, and double shear, southern pine, 1.5 inch main and side members, you see that we calculate the exact capacities here, 1M, 1S, 3S, and 4, that we showed earlier in the slide for the capacities. And again, you take the one that controls. So everything's consistent. You've got lots of tools to calculate those capacities. This one, we did a single shear or a single connector. I didn't take any of the adjustment factors. We do show the load duration, moisture, and temperature factors here, but for being able to compare apples to apples, I didn't take those adjustments. I just used a single fastener value unadjusted, so you can see we come up with the same results. So we've got 6 bolts on each side of the splice, times that 2,300 pounds, times a load duration factor of 1.25, a geometry, or I'm sorry, a group action factor of 0.97, and a geometry factor of 0.57 to give us a total capacity of just under 10,000 pounds, 9,500 pounds for this connector. But we're not done yet. So we've got a couple more calcs to look at, and I'm going to ask Marcy to come back, and we'll take another poll question before we jump into that next section.
Absolutely. All right, so the perp to grain distance between outermost fastener rows shall not exceed 5 inches for sawn lumber under what conditions? Is that never under any circumstance, unless detailing provided for cross grain shrinkage, when the wood is less than 19% MC, or none of the above? So go ahead and vote. About 10 or 15 more seconds. This one is a tough question, so I'll give you a little bit of extra time. I've got about 70% voted, so I'd like to get to 80. All right, I'm going to go ahead and close the poll. Share it. All right, so 53% said B, unless detailing provided for cross-grain shrinkage. 21% never under any circumstance. 15% said none of the above, and 11% said when the wood is less than 19% MC. All right, and Buddy, the truth is?
Okay, so the answer is B, unless special detailing is provided to allow for cross-grain wood shrinkage. And so, you know, in some of the seminars we've had in the past, folks say, you need to ask harder questions. You need to ask harder questions. So we're trying to sort of ramp up the difficulty, but I do see we still have a sharp group here, more than half. Got this correct, and so if you take a look carefully at those provisions and allow for that cross-grain shrinkage, you could do that with slotted fasteners. You could break that up into 2 different plates, like the splice plates we showed in the diagram before. You can then provide for that spacing between outermost rows to be greater than 5 inches. Also, something new to the NDS is an allowance for glued laminated timber to actually have a larger than 5 inch distance between those as well. So take a look specifically if you're using glulam timbers. All right, Appendix E. So I said we weren't done. We came up with a capacity of 9,500 pounds, and we've got about 10 minutes to the top of the hour. I want to let you know that what we will plan to do is similar to what we did last month with our seminar. It'll probably take me close to the top of the hour to finish up the content of this webinar, and then we'll have Marcy close us out, and we'll come back for Q&A after the top of the hour. So if you want to stick around for some Q&A, we'll do that for about 10 minutes or so afterwards. And that way you make sure that we have some time for that, and folks that have other plans, you'll still get your 1 hour CEU regardless if you stick around to the top of the hour. So let's go jump to Appendix E and look at net section capacities of this particular fastener group that we've designed. So to do that, we're going to need some lumber design values, and for that we're going to go to the NDS supplement table 4B, and we're going to need a tension value, of shear value, and a modulus of elasticity. For number 2 Southern Pine, that ends up being 450 psi for tension, 175 psi for shear, and 1.4 million for MOE. We also have to look at our adjustment factors for lumber, and we've got a load duration factor of 1.25 that applies to tension and shear. If we had a wet service condition, that would apply to tension, shear, and E. But in this particular case, we've got a normal moisture environment, a normal temperature environment, and we have an incising factor that might also be applicable. Some of you folks out on the West Coast or that are using Canadian species might need to be aware that if it's a treated product, a preservative treated product, a lot of times they require incising to get those preservatives to penetrate, and so there's an incising factor that goes along with any treated product that has to be incised, and that would affect these design values for lumber as well. So we'll start with a real simple one, and you see the diagram down here in the bottom right of the slide. There's a dashed red line through the bolts. We're just going to look at a net section tension check here, and that's nothing more than determining the cross-sectional area minus the bolt holes and allowing for 1/16 inch oversizing of those bolt holes. So if you were to look at NDS 12132, you see that we allow up to a 1/16 oversizing. If you've got tighter tolerances than that, obviously you could tighten up your cross-section, but that ends up reducing the net section, and so we're going to take the tension value of 562 psi adjusted for the load duration factor, a 13.7 square inch cross-sectional area with the bolts removed gives us 7,700 pounds. And if you remember the capacity we calculated for the bolts, that was around 9,500 pounds. So already we see that net section tension controls this particular fastener or joint. Now let's check row tear out. In this case, we're going to use shear values, and we're going to need the thickness of the member, and then the S critical is the critical spacing or in distance between fasteners. And so in this case, it's 4 inches based on the configuration that we have. Number of fasteners is 3. And so we run through those calcs. It ends up being 3,900 pounds for one row, 78, almost 7,900 pounds for 2 rows. And so that's the row tear out capacity. Then the group tear out is kind of a combination of the two that we've already looked at. So in this case, we're looking at the net section tension here between these bolts, these bolt rows, and then the shear line that would form along the length here. So think about this for a second. The closer you space these rows together, the less tension capacity you end up with right here at this location. So, we mentioned that this is kind of an art because, we have to probably keep these rows at 5 inches or less, so that's automatically going to sort of max out your tension capacity of a lot of these joint configurations. And so when you start calculating this and looking at what controls, this one actually ends up controlling at 6,400 pounds. If you look at this this summary slide here, we calculated a bolt capacity of all the individual bolts of 9,500 pounds, net section tension, row tear out, and then group tear out of 6,400 pounds. So depending on how those bolts are configured, you can move those around, and any one of these could end up controlling. So again, connection design is very much an iterative process. So let's jump then to one final poll question, then I think we'll have a little bit of time for some Q&A before we wrap up.
All right. So the NDS Appendix E provisions focus on which of the following? Is that local stresses around fasteners, end and edge distance and spacing, group action, or none of the above? All right. I've got about 10% voted, so let's get 80% voted again. And since we're at the end of the hour here, let's make that quick. All right, I'm going to give you about another 10 seconds. All right. And then to share the answers. All right, about 41% say local stresses and fasteners, 37% say group action, 16% end and edge distance and spacing, and 6% say none of the above.
Okay, so we are showing some tougher questions here in this particular webinar, and that may mean too that I'm not doing as great a job explaining things as I probably should have, but what we just focused on in Appendix E is purely looking at local stresses around fasteners. That's the net section check that we're going to do for these fastener groups. The end and edge distance and spacing really is part of determining some of the adjustment factors that we looked at earlier, like a geometry factor. The group action factor that we talked about earlier really is dealing with load distribution among the fasteners themselves. So we still had a larger number get this one right, but I guess we are asking some tougher questions. So let me just wrap up the main part of the webinar here, and again, we'll stick around for some Q&A afterwards, but this Technical Report 12, and you see the link there in the bottom of the slide, provides some background and derivation of the mechanics-based approach that's used in the NDS. It does provide some additional flexibility and broader applicability to the NDS yield equations. It's something you could program. It gives you a good sense of how those equations are derived and used. What it does allow that you can't do with the yield limit equations in the NDS is you can account for gaps between members. So if you had gypsum board, for example, sandwiched between two wood members, and you wanted to know what that does to your capacity, then you could calculate that as a gap between two wood members. If you had a wood member with a hollow cross section, like a hollow tube, a hollow steel tube, you could calculate that as well using this approach. And so the Technical Report 12 is for someone who wants to really get down to brass tacks with the NDS yield limit equations, or go beyond those yield limit equations to give you a real rigorous approach for connection design. So I'm going to stop there because we're close to the top of the hour. And Marcy, let's see. And let me talk a little bit about some of the other tools that are available. We get a lot of questions about, is there software available to help me with design? And for this particular topic, connection design, our partners up in Canada have developed a Woodworks software suite. There's a connection module that's part of that, and so you can download demo versions of this. There is a discount for AWC members, but we don't have any financial interest in the software at all, so you need to know that as a disclaimer from us. We are technical advisors to them to help them make sure they get it right according to the NDS, but we don't have any financial interest in the software. There's also, if you're an educator or a code official, you might want to ask about some free versions that are available for those folks. But there is a demo version available, and here's some of the links where you can go to get tech support or sales support for the software. And I'll let Marcy talk to you a little bit about some other resources that are available.
Sure. Our partner organization, Woodworks, provides wood project assistance and other resources. If you're looking for wood project assistance, go to their website, that's their email, help@woodworks.org, or visit their website at woodworks.org, as outlined here on this page. And then to help design professionals stay informed about technical issues affecting the wood industry, we provide a design professional membership. This is a paid membership. There are benefits beyond just publication discounts, so go to www.awc.org/membership if you're interested. And then we also have a special program for our code officials, specifically for qualifying code officials, and there's just listed here some benefits of that program. If you are a qualified code official, we'd like to encourage you to sign up online at www.awc.org, Code Connections. All right, and then just real quick, remember that following today's webinar, you're going to be sent an email. Give me about a half an hour or more to process the reports and get the links ready to send out. And remember that the short survey for a chance to win a free publication, look for information about your certificate of completion and continuing education credits. I know we said about the poll questions, I'm probably not going to be able to get to those until tomorrow, so give me a little time to process those. The certificate of completion and continuing education credits, those will come within 2 weeks of the webinar. Remember, you must have been present for 90% of this webinar, which was 54 minutes. And finally, remember our upcoming event, the March 17th Construction Fire Safety Practices webinar, and then our self-directed study program, as always. And if you're interested in booking a live presentation for a large group in your organization, please contact us at education@awc.org, and that covers my information. So thanks, and have a great day from me.
Thank you, Marcy, and I'll ask Michelle and Lori to come back, and let's take a few questions here and see what we might be able to clarify for today's webinar for folks.
Hey, buddy. We got a lot of good questions today. There was one that several people asked regarding how do you tell which member is the main member in a bolted connection?
Okay, good question. One we've kind of kicked around here in the office as well. For the most part, because bolt has both a head and a nut, I can probably say it doesn't matter a whole lot. Now, the whole thread issue may affect that a little bit. But the principle for the threaded fasteners, it's a little easier for the threaded fasteners, is that the main member is always the one that holds the threads for a threaded fastener. So if you use that same logic for a bolted connection, it works, but you're probably going to get the same result either way if your threads are far enough away from the shear plane.
Okay, great. We had another one. They were asking about if in Table 12A, I had a couple people ask this one, we have the headings in the bolt table. There is Z parallel, Z perpendicular, and then we have a Z perpendicular for side and main members. Can you elaborate a little bit more on the differences on those headings in Table 12A?
Yeah, that is a good question. Let me Actually, don't look at the screen because it'll make you dizzy. I'm going to just rifle back through my slides and see if I can get to this figure right here. So hopefully that'll show up here for you folks in a little bit. This is figure 12G of the NDS. And so I went through that maybe a little too quickly, but the one on the left here is a Z parallel configuration. So both the main and the side members are loaded parallel to grain. The 2x members, this is the longitudinal axis of those wood members. Think of these as 2x12s in the example that we looked at. And so they're both loaded up parallel to grain. You see the load cells at the end, so that's a Z parallel. Now if we were to take these load cells and put one of them up here on this main member and the other one down here on the side member, so that now both the main and the side member are loaded perpendicular to grain, and that's a Z-perp configuration, and that's going to be the fourth column that shows up in those bolt tables, Z-perp. Then over here on the right is the table, or is a figure that shows ZS-perp, and what that means is the side member is loaded perpendicular to grain, so you see the load cells on the side member and it's loading it up perpendicular to grain, and then the main member here is loaded parallel to grain, so this is the longitudinal axis of that main member, and it'd be just the opposite for ZM-perp. So hopefully that clarifies it a little bit for folks.
Okay, great. We had another one. So we talked about that 5-inch maximum row spacing for bolts. When you have 3 rows of bolts, is that 5-inch spacing reflected as an outside to outside dimension, or is that the individual spaces between, or is that the spacing between the individual rows, rather?
Great question, and the short answer is it's the outermost rows. And I apologize for flipping through slides here. I'm trying to get to the one that I know shows the end and edge distances and has that table. So look away from the screen until I get there because the slides are jumping around. Okay, so here we are, figure 12H. And we can see here in this drawing, figure 12H, the note that says spacing between outer rows of bolts. So if we had a third row down the middle of these two, it would still be those outer, that outer row of bolts. And the thinking there is that, think about it in terms of if this were one solid plate here instead of 2 smaller plates, and we have an outer row here and an outer row here, and this is a glulam beam that's 2 feet deep, and it shrinks 2% because of it's getting down to equilibrium moisture content. That could be a pretty substantial shrinkage and could cause splitting along that middle of that glulam beam. And so one of the solutions is to break it up into 2 plates like we see here. You could go also with slotted bolt or bolt holes in the plate on the side, and that would, if you had vertical slots, that would allow some of that movement to occur as well if you can accommodate that kind of slotted fastener for this particular joint. So hopefully that clears that up a little bit more too.
Okay, great. And we have one more. Can you comment on why Appendix E would be considered non-mandatory, even though it often controls, as it did in our example today?
Great question, and one I'm glad to clarify. So we give an approach that could be used, but there's nothing to preclude another type of analysis. If you have finite element modeling software or other engineering approaches that you feel are more appropriate, we don't want to preclude those from being used. This was one approach per Principles of Engineering Mechanics that we felt gave someone an idea of how to use that. The real enabling language, though, is in the code where it says that you need to account for those.
A lot of good questions coming in here. Let me see.
Yeah,
Buddy, this is
Yes.
Michelle.
Okay.
So that, I think there was a little overlap in what you were saying and what Lori was saying, that there is mandatory language in the NDS that says that the designer needs to look at that
Yeah.
mode of failure, right?
Yeah, and let's get there. So I can't remember where that shows up in the slides. Look away from your screen. Sorry about the jumping around, but I think it's pretty close here. And it's in chapter 11 now.
Right,
And
that used to be 10.
Yeah, it used to be 10. So right there. So 11.2.2 is where it says that local stresses using multiple fasteners shall be evaluated. And there are other parts of the NDS as well. I think chapter 2 or 3 that says you got to account for net section where you're taking out any part of the cross section of the member with bolt holes or things like that. So there are a couple of different places that call that out. This just gives us one approach that designers can use as a way to evaluate that.
And there's one more clarification related to the outer rows that I wanted to mention. I think it was mentioned that 5 inches, but for glulam timbers, it's actually 10 inches.
Yeah, that's great. I probably mentioned that very briefly in passing, that that is a new provision in the NDS. Because glulam comes in or has a maximum moisture content at fabrication of 15% versus a 19% for lumber and timber. The glulam folks felt it was more appropriate to ease the restrictions that we have for lumber and timber, and so you can go as high as 10 inches between those outermost rows. That's a good clarification as well, Michelle. Thanks.
Right, and that's only for bolts, not for lag screws or
no, hang on. I don't know that that's true. I think that is for
I'm looking at the table.
large diameter fasteners, greater than a quarter inch, right?
I'm looking at table 12.5.1F.
And tell me what that says.
It singles out bolts for 10 inches, and then for all fasteners, 5, for lag screws and drift pins, 5.
Ah, okay, good. Thanks for clarifying.
I'm sorry, 6. I gotta have my glasses on.
Okay, good. Thanks for clarifying that for everyone on here. So, all right. Well, I think that's a wrap for today. I want to thank everyone for being here and participating, and we'll hopefully see you next month for construction fire safety practices. Have a great day.